All right, so today we're going to talk about heteronuclear diatomics. Okay, so this is the kid that's drowning over here on the left. This one here. Okay, and then we'll eventually get to the other small molecules. Okay, and so today we're doing the C infinity V molecules, not the D infinity H molecules. And so these are still linear, and it'll still be easy to sort of see um, the atomic orbitals that mix to make the molecular orbitals. And then we'll do a little bit of experimental data in terms of how we determine the levels of mixing and so on. So here's the character table for C infinity V. And whenever you're mixing the atomic orbitals and the molecular orbitals, it's good to keep track of the symmetry of those things, because things of the same symmetry will mix. Things of different symmetry won't mix. And so we have different orbitals. S orbitals and sigma bonds will be z squared. Okay. The px, py, and pi bonding or whatever will be x and y type orbitals. So they'll be E1s. And then the pi star, that's that plus minus pattern that we see. Those would be these x, z, or yz symmetries. And those would also be E1. So if you were confused about those for this type of molecule, it's not going to matter because those both fall under E1. You'd still get the same symmetry. But it's really important, I think, for you to be able to pick out, like the pi star bonding would be XZ or YZ, depending upon what plane it's in. And then the pi bonding would be X or Y. We'll see some pictures of those. And then the PZ, the end on the PZ orbitals interacting with an S orbital or with another P orbital would be Z and sigma star. Okay. And so let's build one. Let's build a heteronuclear diatomic. Let's start with one of the easiest ones. Let's take fluorine and bond it to hydrogen. Okay, pretty simple stuff. You've got the atomic orbitals on fluorine, the 2s, the 2p, x, y, and z, and then you've got this 1s orbital. Now, if you're making a heteronuclear diatomic MO diagram, you've got to put the atomic orbitals on both sides, right? And so how do they rate next to each other in terms of energy? So what lowers the energy of an orbital? Getting those electrons closer to a nucleus and having that nucleus be more positive. So the fluorine has how many electrons in it? I mean, how many protons? 9 protons. So it's going to draw those electron orbitals lower in energy. So you see the fluorine orbitals are lower than the hydrogen 1s. And so if you look at those, let's say we were making carbon monoxide. Okay, both of them have 2s orbitals. Which one is going to be lower in energy, carbon or oxygen? Look at the periodic table. Oxygen has more protons, so the oxygen one is going to be lower in energy than the 2s on the carbon. Okay, same with the two P's. The oxygen 2P's are going to be lower in energy than the carbon 2P's because there's more protons. They're going to pull those electrons closer to the nucleus. We have a lower energy molecule. Okay. And so let's mix these orbitals together. So this first, the symmetry, the 1s orbital, we just in the previous slide talked about the character table. So that's going to be an A1. And so is the 2s. It's going to be an A1. And then at 2pz, the pz is going to be A1. So those are your 3 A1s, and those are going to mix together. So how do we mix all of these? Well, and then the px and py are going to be E1. That's a pair, and that's E1. And there's nothing on the hydrogen to mix with that's E1. So the hydrogen won't interact with the px or the py. Does everybody agree with that? I mean, does that make sense to you? Okay, so here's that 2s on the fluorine mixing with the hydrogen 1s. Notice it doesn't drop very much. So this is, let me draw this. See how it drops just very little? Small amount. Think about the particle in a box. That's why I taught the whole first 6 weeks, particle in a box. What lowers the energy? Making the box bigger, right? And so this is telling you that that 2s orbital is really not stretching very far out onto the hydrogen. It's not getting that much bigger. So because these are so different in energy, the 2s really doesn't interact much with the hydrogen 1s. It interacts a little bit. And so because it interacts a little bit, it stretches a little bit over and it drops a little bit in energy. But it doesn't drop a lot in energy because those orbitals are far apart. So the closer together the orbitals are, the more the jump and the more the drop. So they come in and they split up and down. And if they're right at the same energy, they'll split the most. If they're offset a little bit, this one will go down a little further and this one will go up a little bit more. But it's not going to be huge. So that's just the sort of pictorial analysis of this. And then we have the PZ orbital interacting with the 1s, and it drops more. So there's more interaction, more of a drop in energy. So this is a bigger drop right here. Drop. Oh, I can't spell with this tablet. A big dot is what it looks like. So I'm saying big drop equals big interaction. And so that means that PZ orbital is really stretching out and absorbing that other nucleus on the hydrogen. So it's able to get more. That electron cloud has now got two positive centers, and those electrons are going to be happier. They're going to drop in energy. And then up here we've got a big box, but we've got a bunch of nodes. And so we've got 3 nodes here. So this is pretty straightforward, just very similar to the particle in a box wave function. We've got 0 nodes at the bottom, 1 node in the middle, and then up at the top we have 2 nodes. So you can see those different nodes. This is a big, it jumps up. So this hydrogen 1s here, it's moving up a comparable amount to this antibonding orbital. Okay. So you can see they came in like this, and this top one got higher and this bottom one got lower, and then we have the molecular orbitals in the middle. And so these are the pictures. Any questions? These are all sigma. What makes them sigma? Well, yeah, probably. You could think of it that way. What else? There's a symmetry thing about the sigma bonds that's different than the pi bonds. What kind of rotation? That it has rotational symmetry? Is that what you're trying to think of? Like it's the same as you rotate it around, right? These are all the nodes either break or the nodes, sort of chop this cloud, but there's no nodes that contain the bond. Whereas the pi bonding or the p-type interaction, you see this node here is along the bond. Whereas these nodes are all 90 degrees to the bond. Do you see that? So the sigma type interactions contain the bond. They're not above and below it. So they contain the bond, and you can spin around a sigma bond. You know that from organic chemistry. If you take a double bond and you excite the antibonding orbital, then now that bond can spin around the sigma bond. So the sigma bond has rotational symmetry. It can spin one atom relative to the other, or a methyl group, or whatever, because it has rotational symmetry. Whereas the pi bond doesn't. The pi bond has above and below, and if we try to break that, you're breaking the interaction. Okay, now the px and the py on the fluorine come across, and they truly are non-bonding. So went ahead and labeled those with N because there's no interaction with the hydrogen at all. So in this particular molecule, there truly are non-bonding electrons. But it doesn't really, it just really doesn't lend itself to the whole bond order calculation. Because this would look like if you calculated this down here as a sigma bond instead of a non-bonding, if you did this with sigma, I would agree with you that that looks like a sigma bond, and it's bonding. There's no nodes that break the bond, and so I would say this is 2, 4. So 4 bonding electrons, 0 antibonding electrons. Divide by 2, it looks like a double bond. So HF double bond. Well, that doesn't make really any sense because hydrogen can't double bond, right? And so then it makes maybe sense to call this one a non-bonding orbital because it only moves very little. And so then we have 2 electrons in a bonding, 0 antibonding. So then we had a bond order of 2, okay? And then we've got our 6 non-bonding electrons. But again, we're trying to wrestle with this concept of bond order. And bond order really only works well with the homonuclear diatomics. It just, when you get into different kinds of atoms, you get into larger molecules like water or CO2, the bond order just breaks down. And there's just really no good way to calculate it. So it is great to calculate that for the homonuclear diatomics. We can see that it confirms molecular orbital theory in terms of the force constants, bond lengths, and so on. But here with the simplest heteronuclear diatomic, it already starts to get confusing because it's starting to mess with our labels. You know, I would have labeled this as sigma, but if I label this one as sigma here, then I get a bond order of 2. And that's I don't like that. And so I'm going to just come back and erase that answer and put in a non-bonding there, and then I get my bond order. But that doesn't feel good. You know, that we should have a more clear way to define these things. And so the whole concept of labeling them sigma and sigma star, pi and pi star, it works 80% of the time, I'll say. Yeah. And that's not satisfying. So again, these non-bonding electrons are non-bonding, and so we would just only count these 2 right here as the bonding electrons. Okay. And then here's the ionization limit up here. So if we take this molecule and we start blasting it with UV light, we'll get photoelectrons out. And if we measure the energy, the binding energy of those photoelectrons, if we had fluorine atoms, we would get 18.6 electron volts for the 2p orbitals. And we had hydrogen atoms, we'd get 13.6 eV for the 1s orbital. And then if we hit this molecule with the same light, we see that it drops, 0.2 eV to 18.8. And then we get 18.6 for those fluorine non-bonded electrons. And then we could even, if we were able to excite this molecule, so we hit it with light to excite one of the electrons to the sigma star, and then we hit it with light again and measure the energy of that electron that comes out. We can get that excited state. And so there's a way to capture that. Even though there's no electrons in the ground state molecule, if we were to excite this molecule and then kick that electron out, or if maybe we made the anion, if we put a negative version of this molecule, then we would be able to measure that antibonding orbital at 13.4 eV. So that's also how we know the relative locations and energy of these orbitals. Okay, so again, the data supports the molecular orbital theory of the structure of the electron cloud, which is the electronic structure. Okay, so let's look at carbon monoxide. So I went ahead and calculated this one in Gaussian. And you can add this keyword to Gaussian. If you're building this in Gauss View, down there at the bottom, before you hit submit, there's a little box that says additional keywords. And you could just type this in there. And what that does is that calculates the full population of all of the orbitals. And it tells you all of their energies and prints it out. And so then we get all of the energies here. So we did the atoms and we did the molecule. So here we can see all of these negative energies are occupied. So it even says O and V. The virtual orbitals are the unoccupied ones. And then I do the molecule and get the same kind of output. And so let's look at our MO diagram. So here's the carbon monoxide molecular orbital diagram with core electrons. So what we just said earlier holds true. If I've got an oxygen atom with what is it, 8 protons, that's pulling that 1s way down. So look at the 1s on the oxygen versus the 1s on the carbon. Notice they don't mix. This is the same energy. It comes straight across, and this one comes straight across. So do not do what's in so many of your freshman textbooks. They're absolutely wrong, and I've written the publisher sometimes, just depending, they never do change it. They will show this. They'll show the 1s, and they'll show the bonding and anti-bonding versions of the 1s. And this whole thing is absolutely not true. No. Why? Because they're too close to the nucleus. So as the atoms come close together, it's the frontier electrons, the valence electrons that interact. And the 1s orbitals are sucked in so close to the nucleus, it really doesn't know that the 1s electron orbital on oxygen does not know really what's happening out on the valence shell. So the 2s and the 2p are mixing, but the 1s is not. So do not show the core electrons mixing into making molecular orbitals. It's only the valence shell orbitals. Same here with the 1s on the carbon, much higher in energy because there's fewer protons, only 6 protons. And so it's not changing. No change, no mixing. No, what do we call it? No mixing. Do y'all understand what I mean by mixing? The orbitals are mixing together and making molecular orbitals. So these are just atomic orbitals, no mixing with the other atom. Okay. Okay. So then let's zoom in up here. So we come in up at the top. So we're going to just zoom in on the valence shell area here. So here's what Gaussian gave us. And now Gaussian's very picky, right? We give it the freedom to calculate the individual orbitals, energies, and it's broken the degeneracy of those p orbitals. We should have 3p orbitals. If you're drawing it by hand, you would just draw, you would draw 3 equal energy p orbitals, right? But we gave Gaussian the option, and it calculated the energies of those, and they're not exactly the same energy because 2 of them are occupied and this one's not occupied, and so it has a slightly different energy. The 2s is here. Look at what happens to the oxygen 2s. It's way down there because there's 8 protons, and so it pulls that 2s down, pulls the 2p's down. We've got 2 orbitals that have 1 electron each, here and here. Notice how they're lower in energy than this orbital that has 2 electrons in it because those 2 electrons are sharing the same orbital, so the electron repulsion is making them go up a little higher. So it's just not as energetically favorable. Now it's color-coded. I've got the X and the Y. You see the green here. That's the row of the character table, the E1 row. And then the A1 rows are the 2 S's. And so then we can mix those together. So the Z, the PZ, and the 2 S's are A1. So these on this side, on the oxygen side, mix to form those 4. Okay. Along with these. So we come in with 4 atomic orbitals, 2 on each side, and so then we make 4 molecular orbitals in the middle. And so if you're making this diagram, you can just draw your 4 lines. Draw one down below the 2s here. Okay, so you would draw this one down below, and this is the highest this is the 2pz, so go up a bit and draw that one. That's going to be your highest one, and then just draw 2 in the middle. I mean, it doesn't matter because I'm not getting a ruler out and measuring your energies, right? So you just draw 2 lines in the middle somewhere, and those are your 4. A high one, a low one, and 2 in the middle, and you got your 4 molecular orbitals for the A1 group, okay? And so those are going to be with our diatomic, probably our sigma, sigma star, sigma, and sigma star. And then I went ahead and put the electrons in there. We had 6 electrons, so the bottom 3 are going to be populated. Let's bring in the pi. Okay, so here we have the 2p's, x and y. Again, on these, the 2p on the oxygen, I would just come down and draw two lines, and then on the carbon, the 2p, x and y, I would just go up a little bit and draw two lines. And so we have those two splitting down and up, okay, and mixing. Now, as far as putting these above or below, that's that question of SP mixing, and I tend to put them above the sigma. Only on like carbon and lower would they be, those pi bonds would be lower than the sigma. But I'm not going to count off for that, because again, you would have to do a calculation to know whether they're above that sigma or below it. Okay, so we could disagree on that. And so then we have these pi and pi star interactions, put the electrons in. We have 4 electrons coming in, so the 4 electrons go in those bottom 2 orbitals. And so there's our MO diagram for carbon monoxide. Now let's think about this. If we were to draw the Lewis dot structure for carbon monoxide, what would we draw? Well, we'd probably do the octet rule, because it's carbon and nitrogen and oxygen that require an octet rule. So if we do that and calculate, the octet rule, we have a triple bond, 2 non-bonding electrons on the carbon, 2 non-bonding electrons on the oxygen. And what that gives us then is a formal charge. So do y'all remember how to calculate formal charge? Okay, let's just do that real quick. So I don't like divorce, but this is a good analogy. So for formal charge, if these carbons and oxygens are going to get an equitable divorce, they're going to split every bond into 1 electron each. Okay, so it's got triple bonds. So for each of those bonds, each of them takes 3 electrons. Okay, and so this oxygen can claim 1, 2, 3, 4, 5. So 5 electrons claimed. So, but it brings in 6. So oxygen brings in 6 valence electrons. And it can claim, you subtract the number it can claim. Okay. So the valence electrons minus the electrons it can claim in the molecule, we get a +1. So that's the formal charge. All right, let's do the carbon now. So carbon, it has 2 non-bonding and 3 bonding. Okay, so that's 5 claimed, but it brings in 4 valence electrons. Minus 5, I'll call it CE for claimed electrons. So I can't say bonding because there's 2 non-bonding, so I'm just calling it claimed, how many it would take if it got a divorce from the oxygen. Okay, so then that's a -1, formal charge, FC. So that's a review of how to calculate formal charge. Now, it's nice to reduce the formal charges. I mean, if the carbon really is negative and the oxygen really is positive, maybe it wants to get rid of one of those double bonds and put those electrons on the oxygen. Oxygen has 8 protons after all, and so it's going to want those electrons more. And so if we move that double bond back to the oxygen, we lose our octet rule, but we reduce the formal charges. So a lot of times in our freshman courses, we don't do carbon monoxide, because when we start talking about formal charge, then we end up with this molecule here, which does not have an octet for the carbon or the oxygen. Carbon has 2, 4, 6. It can claim, I mean, like if you're calculating for whether it has an octet, it counts 2 electrons per bond. So carbon gets 2, 4, and then it has 2 non-bonded, so 6 electrons. Oxygen has 2, 4 for the non-bonded, and 6, 8. So it has 8. So it's happy, but carbon's not happy. And that's what would cause us to make a triple bond if we were going to stick hard to the octet rule. So that's the octet rule versus formal charge fight that they're having in terms of carbon monoxide. Now, this should have a play on the dipole moment of this molecule, shouldn't it? So what does the dipole moment look like in this molecule? So It's definitely got a dipole moment because the two atoms are not the same. So anytime you have a bond between two dissimilar atoms, you've got a dipole moment in that bond. Okay? And so in this case, the positive end is on the oxygen. But in this case, the positive end would be on the carbon. And so that's interesting. So if we do the Gaussian calculation, we can see that the oxygen is a little bit more negative. Okay, so it kind of fits the reduction of formal charge. So this one right here. Okay, but then the bond length is also smaller than the double bond. So if you look at the bond length, it looks like it's more like a triple bond, but the dipole favors the formal charge. So it's a confusing molecule, even though it's simply carbon monoxide. So that's a little weird. Okay, so this would be close to a triple bond, and the dipole would point towards the oxygen. But anyway, if you're looking at this molecule and you just had to guess which way the dipole moment is, would you think that the negative part of the molecule would be the oxygen? Because it's got what we call more electronegativity. It's pulling electrons towards itself. And so, yes, I would, if I had to guess, I would put the positive end on the carbon side and point towards the oxygen. Let's see if the molecular orbitals that Gaussian produces can help us in this. So here's the molecular orbitals of the molecule. This is one of the ways that Gaussian can display the molecular orbitals in a wire mesh way. And you can see the A1, this lower one, this sigma, is mostly on the oxygen. It does reach over to the carbon, but it doesn't go all the way around the outside of the carbon. Okay. And here we can see see how close this node is to the oxygen atom? It looks a lot like the 2pZ on oxygen. And the 2s on carbon. Can you see that? Like it's got, the carbon is completely surrounded like a 2s orbital, and the node is really close to the nucleus on the oxygen. And so that's 2pZ character on the oxygen and the 2s on the carbon. And those are closer together in energy, so they're going to mix more. The bottom one is mostly a 2s on oxygen and almost nothing on the carbon. Okay. And then these two are interesting. We'll get to them in a minute. We have this concept in inorganic chemistry with bonding called pi donation with back bonding. But let's go ahead before we get into that. Let's sort of characterize the orbitals that figure in. So now we have, major 2pZ. So this is a lot of 2pZ on the carbon with a little 2pZ on the oxygen. Why is there a little bit of 2pZ on here? Because we used up a whole lot of our 2pZ down here. Okay, so it has a big coefficient in front of its 2pZ orbital in this one here at the bottom. And then the coefficient in front of the 2pZ on carbon is bigger on the other one. And then up here, it's kind of equal. So these are if we were to write this one, this wave function would be 2pZ on carbon. This is an equal sign, not a minus. Okay, minus the 2pZ on oxygen. And you see the minus sign indicates that they are out of phase. So we have this node that breaks the bond. Does everybody see that? Okay. Then we get to the pi and the pi star. Those are expected. Those are what we would expect. So let's see if we can show this. This is kind of coming in and out of the plane, and so we call this the PYs. PY. So 2py on carbon plus 2py on oxygen, and this is 2py on carbon. What am I going to write next? Minus 2py on oxygen. You see, they're out of phase with each other, so there's this node that breaks the bond. So they're not mixing. One's expanding into the middle of that bond while the other one is contracting. And then this is the 2px's, same thing. So this is the X version, and these are the Y versions. So those are the molecular orbitals on carbon monoxide. Anything I can clear up for you? Okay, so let's look at these two orbitals here because they're so important. You see, this is the highest occupied molecular orbital. And then these pi stars are the lowest unoccupied molecular orbital, so they're pretty close in energy. And so this is a very important concept in the metal bonding, because what do these metals have in the middle? We just talked about them last lecture. What's a feature of this, like scandium through zinc? See, so far we've been doing our molecular orbital diagrams with like carbon, or like O2, F2, N2. Now we're doing CO. We did HF. We haven't done anything with this middle part except for last lecture. What was so interesting about last lecture in terms of d orbitals? And so this is very important because these two orbitals will interact with d orbitals very well. This is a page out of the sort of the inorganic Bible. Okay, and this is a strong way for these molecules to interact, and this is how they draw it. It's sort of a simplified version of that sigma bond, where we've got this electron in this bonding orbital, and it's coming in phase with this metal cation or metal atom, and it's bonding here. And then this metal also has this d orbital. So the dxy, or it would be a z, xz, or dyz. And the electrons in that dxz can interact with the pi star. So there's electrons in this orbital that interact with that pi star. Now, what does it gain by interacting with that pi star? There's electrons in this d orbital on the metal, and it interacts with that pi star in a favorable manner so that there's overlap and so on. Well, what do you get when you get a molecular orbital? If you're on an atom and you get a molecular orbital, what do you gain? Space. And what does space do? Bigger box, lower energy. So it makes a stronger bond, right? And so the electrons in this d orbital come and they interact with that pi, and now they can run across the whole molecule. They can go not just stuck on the metal, but now they can go across the whole carbon monoxide, and that becomes one orbital that's really big. And so if you have electrons in that dxz orbital and they interact with that pi star, they've got a bigger wave and they drop in energy and you make a stronger bond. And so this looks like kind of like a pi bonding interaction between the metal and the carbon monoxide molecule. And so this is such a strong interaction. This really revolutionized what they call organometallic chemistry. So organic molecules interacting with metals. This d orbital interacting with this pi star orbital allowed organic molecules to stick to metals. That's really cool. We can get metals to go into organic solution. It's no problem getting metals to go into water, right? You make a cation, water just surrounds that thing with oxygens and pulls it into water. We make aqueous solutions with metals all the time. How do you get a metal to go into gasoline? An organic solution. It doesn't like gasoline. Gasoline doesn't like it. There's no interaction. You get some carbon monoxides around that metal, so you make a chromium hexa CO, put 6 carbon monoxides on there, and now it's soluble in organic solution. Or you can put other kinds of molecules that have these ligands, is what they call them, latch onto that metal and pull it into organic solution. Now, why do we care about doing that? Well, we can take crude oil out of the ground, and it's brownish to black. There's some yellow crude too. The dark color comes from double bonds. Okay, double bonds increase the reactivity. They increase the boiling point, and so on. And so, if we want really lightweight oils, we want to get rid of the double bonds. One way to get rid of the double bonds is through catalysis. Metals can catalyze the hydrogenation of those double bonds and turn darker oily oil with a low boiling point into gasoline. And so Wilkinson, the author of this book, has made Wilkinson's catalyst to crack those double bonds and move it from like diesel into the gasoline range, where they could sell more gasoline, and just a few percent change of that yield was worth billions of dollars. And so he made a rhodium catalyst using this kind of idea of this bonding with d orbitals and atomic orbitals on these organic molecules to get that to go in and basically revolutionize the production of gasoline from crude oil. And it's another thing too that was good about that is those are the more useful fuels. The heavier oils are useful for lubrication, okay, but you've got this much application for lubrication and you've got this much application for combustion. And so making a lighter fuel that is more useful that was revolutionary. Okay. Now let's get into the most complicated molecule that we'll deal with this semester, and that's the ethene molecule. So again, local bond theory produces sp2 hybrids and all of that, and there's 3 types of bonds. And so we talked about predicting that there'd be 3 peaks in the photoelectron spectroscopy for this molecule, but we end up seeing 6. Now we have this projection operator that your video on Friday is going to talk about on how we get these 4 orbitals for hydrogens. So we have hydrogens. There's 4 1s orbitals on the hydrogens. And without going through the whole projection operator lecture, because we're going to get that on Friday, how do we get these 4 pictures? Well, those 4 orbitals can all be in phase, right? All 4 of them. Can you come up? Okay. There's only 4 ways to do this. I needed 4 hands, okay? So we'll do them side by side. So put your hands right here by mine. We'll come into the video. Okay, let's make sure they're lined up just right. Okay, so these are our 4 hydrogens. Okay, and now they're in phase all together, like this. There's no nodes, right? Now, that's this one. See, it's all the same color. Okay, now let's do the next one. You see that? So mine are going to go big while yours are small. See the node in between? They don't ever hit. Okay, so that's this one. Okay, now we're going to be talented here. Okay, so our both bottom ones, open them up. Now there's this. See? So they interact on top and bottom, but there's a node here. Okay, now this is the tricky one. Okay, so stop, do that one. Okay, ready? Go. Okay, so there's 4 nodes. Oh, no, 2 nodes now. There's a node in the middle going horizontal, and there's a node vertical. Did you see that? So those are the 4 1s orbitals, thank you, interacting, the 4 ways they can interact. And you can go through the character table and generate those 4 images, and you'll know the symmetries of them. Like right now, just by doing the hands, we don't know the symmetries of them. But we know one of them is, the top one is plus, minus, plus, minus. So it's going to be one of those X, Y, X, Z, Y, Z ones, okay? And we know this one is the same in all directions, so we know it's top row. And then the others we just need to know. it's oscillating this way, left and right. So we look at the the coordinate system, and that's x. X is going this direction, and then this one is going up and down, and we look at the coordinate system, that's y direction. So we could easily label those with the character table. So those are our four, what they call, listen to carefully, symmetry adapted linear combinations of atomic orbitals. That's right here in the green arrow. Symmetry adapted linear combinations. The linear combinations are 1s on H1 and plus 1s on H2 plus 1s on H3 plus 1s on H4. So that's that linear combinations, right? Plus and minus in front of all of those. Those are the linear combinations of atomic orbitals. And then they're symmetry adapted, meaning that they're given the correct symmetry in the character table. Okay. So those are SALC-AOs. So symmetry adapted linear combinations of atomic orbitals, and those are for the 1s orbitals. Now we could do the same thing for the carbon, the two carbons in the middle, and doesn't it look familiar? It looks like an MO diagram for a diatomic. Because that's what you would get if you had two carbon atoms in the middle. The 2s orbitals would get together in bonding and antibonding. Then the p orbitals on the side-to-side interaction, and then the pz's would get together in the middle, only this time it's a px because it's the x-axis of the molecule and so on. So this whole thing just looks like a C2 MO diagram. So to build a bigger molecule, you just do it sort of pairs at a time or identical atoms at a time. So there's 4 hydrogen identical atoms, and so you do them as a group, and you do them with all of the combinations. And then over on the left side, you do the 2 carbon atoms. Those are identical atoms. You do those 2 as a group, and you end up with what looks like the C2 MO diagram. And then you bring these 2 diagrams together to make the bigger molecule. And so it does look confusing, but there's a poster out here on the hallway that I had. I made this up and I printed it out, and so you can go up there and you can look at all the fine print. It's also available on Blackboard. So let's zoom in. So this is the projection operator SALC-AOs for carbon-carbon. And then we make these things in the middle. So they produce these MOs for ethene. And this is what we end up with. All the different pictures. And if you zoom in, they should make sense to you, looking at how they interact. And so what I would like for you to do, and I'm going to make a Kahoot for next time, for Wednesday, you should be able to look at this and tell me the orbitals that contribute to it. Okay. So let's try that for this orbital here. Okay. So this wave function is equal to, and let's draw our coordinate system. We said that, what do we say? Y was up and X, yeah, so this molecule Y is up, X is here, and Z is coming out of the board. So which orbital is the carbon bringing to the table? So think about this carbon atom and look at the colors around that carbon atom and tell me which orbital you think is being used from that carbon. It's good. It's a p orbital. Okay. So that's good. Can we see that? Because there's a node going right through the carbon. So we got a node that is carbon sitting on a node. So it has to be a p orbital. And an s orbital, carbon's not sitting on a node. So if it's sitting on a node, that's a p orbital on carbon. It's a 2p orbital. So we'll do this. We'll say 2p on carbon, but which p is it? I want to know that subscript. Yeah, look at the coordinate system. This is right here, the y. So it's 2py. Okay, now, question mark. Let's do the other carbon. Do I do a plus sign or a minus sign? There's no node breaking between the 2 carbons, and so we want a plus. Yeah, so we're going to say plus. And what's the orbital on the other carbon? Same one, yeah, 2py, good. 2py on the carbon. I could do carbon 1 and 2. Let's do that. Carbon 1 and carbon 2. Okay, now we get to the hydrogens. And this is where I guess this, I don't know. When we did the chromium, remember we did the chromium and it was plus 6 hydrogens or plus whatever. I want to show that there's no nodes breaking these things. And so I would just, we could just say for 1s is on the hydrogens. Because it's just showing that we're in phase with all of them for 1s on hydrogens. That's sort of cheating, but my main point was which orbitals on the carbon are we using here? And I'm showing the plus sign here. So we don't really have to get into like which hydrogen is A and which one is B and C and D, but this is, could you get this? Yeah. Okay, what about this one right here? It's the same designation, but there's only one tiny little change. Yes. So this wave function is equal to 2py on carbon 1 minus 2py on carbon 2 plus 4 hydrogen 1s. I would be happy if you could do that. Okay. What about this one here? 2pz carbon 1 plus 2pz carbon 2 and 0 hydrogens, because hydrogens don't have 2p orbitals. So even though it's above and below the hydrogen, there's no p orbital on the hydrogen for that to interact with. And so the node is cutting that hydrogen. The s orbital can't interact with that. And so it's going to just be that, no hydrogens. Which orbital is this one using? Just give me the carbon orbitals here. Look at it's the X one, right? It's going along this axis here. So that's the 2px's. And I would draw that as a plus because they're interacting in the middle. They're in phase. So I would call that one psi equals 2px carbon 1 plus 2px carbon 2 plus 4 1sh. So that's this one right here. Okay. So if y'all can do that, that would be awesome. Okay. I'm not expecting you to be able to draw the whole MO diagram for ethene, but given that MO diagram, you should be able to kind of understand how the atomic orbitals are mixing in and making these molecular orbitals. That's my goal. If you can do that, you're going to be way ahead in terms of your peers at other universities. You're going to make us proud. Okay. So that would be great, and I'd be happy.